1, minus 4, 1, which is a good start. There's definitely one T32 here, but you need to use the boundary condition, right? We're replacing T52 with this expression. So this expression here, this becomes T32 minus 2Q delta over alpha. Minus 2Q delta over alpha is a constant, and so this part here would move to the right-hand side. So I've got two T32s, right? I've got one here, and I've got one here. So the correct answer was E. I'd put a 2 here, and there'd be a 0 here, a 0 here, and a 1 here. And then over here, I'd have minus 3 alpha, and then plus that 2Q, what was it? 2Q delta over alpha. So sorry, that's minus 3 gamma plus 2Q delta over alpha. Do we have a 298 as well? Yeah, oh, and then one is that. That's a 298 that jumps the other side, so there we go. Questions about that? I recognize that's a little sneaky. Again, nobody's gotten that all day. But we'll use the boundary condition, and that means that there's 2 of these T32s, because we replace the ghost node with the T32 value. Okay. So I could proceed like this and fill out a big matrix. Typically what you want to do is write out enough equations so you can see the pattern in this matrix, and then fill that out and solve the system as, A backslash this vector. So this two-dimensional problem, it does get a little bit tedious to do that, so I'm going to show you a different way, what we call the iterative approach. And so the idea, the general idea behind the iterative approach is that I'm going to go back to step 4. Now you're welcome to do this either way in the project, whichever way you're comfortable with. Last time in the code, we showed you the direct way. Today in code, I'm going to show you the iterative way. And I'm going to isolate spell isolate Tij in the discrete governing equation. So in my case, that is Tij equals 1/4 times Ti minus 1 j plus Ti plus 1 j plus Ti j minus 1 plus Ti j plus 1 plus the gamma times I minus 1 component, close that bracket. All I've done is rearrange the discrete governing equation for Tij, but I'm going to solve this iteratively by putting in initial guesses for the temperature on the right side. I'll call those my guesses at iteration k, and this gets me a new value at iteration k plus 1 on the left-hand side. Boundary conditions we'll see incorporated similarly with the Dirichlet conditions. We're going to initialize Tij at the bounds to be equal to 298. And for the Neumann condition, we're going to add an if statement in the ij loop. And we're going to handle this equation here, make this substitution manually in the case where we encounter a ghost node. So that's the big picture idea of what we're going to do here. Why don't you go ahead and go to the lectures page for today. You can open up the code template to follow along, it's called Laplace.m. Okay, it should have been called Poisson.m, but sorry, Poisson. I called it Laplace. Let me switch to that as well. Okay. So I have this code, the code template that you have. It just sort of defines the setup domain size of 1. So this laptop is a square 1 by 1 system. Rather than 4 nodes, let me do 11 nodes. So a delta of L over 10. So the total number of nodes is calculated as n. And then I pick some values for these constants. Ng here is gamma, my lump connection or collection of constants. So the first thing that we want to do here is set up our boundary conditions. And a useful way to do this is to allocate a solution array. So let me say that we're going to iterate maybe 1,000 times. I can make T an array of size n by k max. So T then has index of x, y, and iteration. And since it's square, this is n here, and this is n here. Once I've allocated my array, it allows me to define the boundary conditions. Boundary conditions. For all x, for the first node in the y direction, let's predefine all these values at every iteration to be 298. All right, so that is going to be for all x, first node in the y direction. This is essentially the bottom edge. We could do the left edge. That would be for when x is equal to 1, for all y in all iterations. Define that to be 298. And then the top would be, again, for all x, when y is equal to the maximum number of nodes, n, at all iterations, hard code that to be 298. So the Dirichlet conditions can be hard coded in this way. Oh, MATLAB's telling me this is colon and a semicolon. Okay. Now we're going to use this iterative method, also known as Liebman method. K goes from 1 to k max minus 1. I'm going to loop over some values. What should be my range of I and j? What values do I need to loop over? Here, I'm going to give you some choices. Should we loop over from 2 to n and 2 to n minus 1? Should I loop from 1 to n and 1 to n? Should I loop from 1 to n and 2 to n minus 1? Or e, something else? Might help to kind of think of this sketch here. It's the x direction, y direction, rather than 4 nodes, n nodes. All right, so I've got a bunch of nodes now. This is the nth node. This is the nth node. This is the same as that previous clicker question. I was essentially asking, at what combinations of I and J, so the I index, Y is the J index, what combinations of these do we need to actually solve or apply our discrete governing equation? This is the same question here. Over what pairs of I and J do we need to apply our discrete governing equation? The pairs are determined by the bounds on these loops. And if you need a hint, the hint is to think about on the left, we're going to have, over here, T, I, J, K plus 1 is equal to stuff. We only need to solve this for the I's and J's for which T is unknown. Let's see what people say. Another couple seconds. We only want the I and J that correspond to unknown values. We depend on a variable. We're saying A, good. A little more than half the class is saying A. The correct answer is A. That's because if this is location 1, 1, I don't need to solve for any of these values. I don't need to solve for any of these values, or there's nodes on the top, or these values. Those are all the ones that are defined by my Dirichlet boundary conditions. There are nodes over here, though, that I do need to solve for. And so in the I direction, I need to go all the way out to N. And in the J direction, you see I'm going to go from something 2 to N minus 1. Let's code that up. I can start here in the I direction at 2 and go all the way to N. And in the J direction, I start at 2 and go to N minus 1. Because I already know my solution at when I is equal to 1 and J is equal to 1. Right? I've already defined that. Those are my boundary conditions here. Clear my drawing so I can write out some code here. So T, I, J at a new iteration value K plus 1 is equal to, what do I say, 1 over 4 times T I minus 1, oops, comma J, comma K, plus T I plus 1, comma J, comma K, plus, then we start iterating across J's, so J minus 1 plus Ti J plus 1. And then I have the plus gamma times I minus 1 term. And close bracket, end statement. Okay. So this is application of my discrete governing equation at all I's and J's where I don't know the temperature. Now the nice thing about the iterative approach to coding this up is I only need one line of code here. I didn't have to work out the equations like we were doing on paper for all the different cases. It is a little bit more complicated in terms of the coding because now I've got an iterative solution. I introduce this whole new variable K. What about our flux boundary condition? Which of these terms is going to cause a problem? Which of these terms do we need to be replacing with our flux boundary condition? This term, this term, this term, this term, or this term? There's a variety of ways to think about this. Go back to your diagram. Think about where does the flux condition arise? Or look at the bounds of our loops and imagine where are one of these indices for one of these terms going beyond the bounds of our loops are going beyond the domains of our problem. In other words, generating a ghost node.